Hello and welcome to this episode of Rocks with Russ, where we sit down and learn the grammar of the language of the rocks. Okay, so today we're going to look at minerals. Minerals are important to us. They are the building blocks of rocks. And here in my hand, I have an actual rock. That's right, an actual rock. You may have seen one of these before. But if you look at the different colors in here, just based on color, you can tell that there's a bunch of stuff in it. And those things, the one thing is not the same as the other. There's pink minerals, there's pink stuff, there's white stuff, there's stuff that looks kind of dark grayish. Those are different minerals. Now I can separate out these minerals individually, and at that point, I'm looking at the words in a sentence. So let's talk about this some more. What is a mineral? A mineral, as a building block of rocks, minerals come in a wide array of categories based on their chemistry. So silicates, sulfides, halides, and so on, depending on what their chemical structure is. But then I just referred to chemical structure. So minerals are naturally occurring inorganic solids with a definite chemical composition, distinctive physical properties, and a crystalline structure. That kind of goes with the chemical composition piece. So naturally occurring they have to occur in nature. Inorganic, they're not produced biologically, they're produced through inorganic processes. So they have to be solids, not liquids or gases. Those three are pretty straightforward. The natural occurring one can be a little fun to play with, but the definable chemical composition and crystal structure, that piece is important. And you can't see that necessarily except in the way the crystals, if you happen to see the crystals of a mineral, the way they play out. So this is an example of that. This is muscovite, and muscovite has a particular structure. It's a sheet silicate, so its chemistry is arrayed in a sheet form in all directions, and so you get this really distinctive physical structure. And this also happens to be one of its distinctive physical properties, is that you can see it's really, really flat, and you can actually see it. It's translucent. See through it, rather. It's translucent. So when we talk about minerals, one of the things you'll do in class is we'll look at how to identify them. And we do that primarily through distinctive physical properties. There are better ways in the lab to more specifically identify a mineral through, say, X-ray fluorescence or something of that nature, but you have to be in a very special lab to have that kind of equipment. So when we're in the lab, we're essentially doing field identification of minerals as best we can. So if I were to do that, there's certain tools I'll go to right off the bat. One of the things I'll do is I'll take biotite, for instance. If I see a piece of this, I will look at its, first I'll look at its luster. Luster is just the way the light reflects off of the surface of a mineral. In this case, it's either generally going to be non-metallic or metallic. There are other varieties of luster, submetallic. There's also various more specific types of luster, where we can say like vitreous or peacock luster, things of that nature. But really, when it comes down to is metallic and non-metallic. And muscovite is a non-metallic mineral. An example of a metallic mineral is galena. Galena here, you can see how light reflects off the surface, kind of like light reflects off of aluminum foil. Or pyrite. This is a really good example of that as well. Okay, so I look at the metallic or non-metallic first. And that helps me, of the 5,000 plus minerals that exist in the world, that helps me really begin to narrow things down. So then what I'll do is I'll start thinking about things like specific gravity. Now in the field, all I can do with specific gravity is sort of hold it in my hand and, and say, for its size, does it feel unusually heavy? And so I would say, well, in this case, pyrite, which is iron sulfide, pyrite does feel unusually heavy, and certainly galena does. Galena is lead sulfide. You can imagine that one probably feels a little heavier than most. And so that's a very sort of really crude way of looking at specific gravity, but specific gravity has a much more technical term to it, and you have to measure it specifically in a lab, so it usually has a number attached to it. But minerals with high specific gravities do tend to be heavier for their size, okay? Because they would be displacing an equal mass of water, and so you're looking at a property that's difficult to measure in the field other than just holding it. So that's the next thing I might look at. Then I might grab a rock testing kit of some kind, and one of the first things I might do is try to scratch glass. And I could keep this in a little pouch out in the field, but I could scratch the glass or I could try to scratch the glass with the pyrite and see whether or not it leaves a scratch, right? If it leaves a scratch, it must be harder than 5.5. Glass is about 5.5 in hardness. If it doesn't scratch the glass, then it's less than 5.5. Plenty of minerals have scratched this glass. Quartz will scratch glass. Quartz has a hardness of 7. And when I say hardness, I'm referring to Mohs hardness scales. Friedrich Mohs came up with that scale. He's buried in Vienna, by the way. Came up with that scale many, many years ago. It's a relative hardness scale, very different from an absolute hardness scale. Diamond is a 10, talc is a 1. In absolute hardness, diamond is a whole lot harder than corundum, which is 9. But when we're looking at relative, it's sort of a little different. So it's just relative to one another, which is harder. It's a very useful scale, even still today. So anyway, hardness. I can also then narrow hardness down further. I can use a penny. That's a hardness of 3, 3.5. I could use a steel nail. That's about a 6. I can also use these handy-dandy concrete testing tips here, and they have numbers on them. And then I can try to scratch the mineral with this. And so if you happen to have those around, those are very useful as well. That's hardness. And again, you're testing it relatively against the hardness of other things. Another diagnostic physical property that I'll use is streak. So I take an unglazed ceramic tile and I take my mineral, I put the streak plate on the counter, and I try to draw something with it essentially. I'm leaving a powdered form of the mineral on the streak plate. The streak plate has a hardness of 6, so if it's harder than the streak plate, it will not leave a streak. If it's not as hard as a streak plate, it's likely going to leave a streak, and the color of that streak, in this case galena, has a dark gray color. And that color is going to be very useful for helping me identify that mineral. Some minerals, like hematite, this one here, will look a certain way but have a certain kind of streak. So hematite has a reddish brown streak, even though this one looks very silver. So sometimes streak is useful, and sometimes it's very useful, but you have to be very kind of careful with it. Another one you'd be careful with is color. So here's an example. Hematite, I mentioned that one. Hematite comes in a variety of forms, and so I have here 2 pieces of hematite, and you can see that color might be a little misleading because it can come in a variety of them. All right. Otherwise, sometimes color is very distinctive. Like with olivine, it's always green, right? So it depends on the mineral. There's a little bit of experience involved here that's very helpful in identifying minerals in that regard. Another diagnostic physical property that's very useful is whether or not it fizzes when exposed to acid. And so if I take this here, hopefully you can see this, and I drop some acid on it. This is calcite, by the way, a really big chunk of calcite, and you can see it, hopefully you can see it's fizzing. So calcium carbonate will fizz under hydrochloric acid, and you can take hydrochloric acid in the field with you and use it as a way to test minerals. And that's a very useful physical property. Another one is cleavage, which I've already been showing you a really good example of. Perfect cleavage in one direction. Cleavage can come in a variety of directions, but it's really all about how the mineral breaks. Does it break cleanly along surfaces that are reflective of the crystal structure, or does it break roughly and in a conchoidal fashion? That's not a great example, but I do have some quartz over here. Quartz breaks conchoidally. You've got some nice crystal faces over here, but you can see where it breaks in this kind of like the edge of a broken glass. There are some other distinctive physical properties that are worth noting. One of my favorites is phosphorescence, and you can see here this mineral, which doesn't look like much of anything, but when I shine a black light on it or ultraviolet light on it, it really kind of glows with excitement. So that's an important physical property. Another one, you've probably heard some beeps in the background. Another one that's a little less common in the lab because we don't let kids play with radioactive minerals, is radioactivity. And so if I turn my Geiger counter on and I bring them closer to this box of unique minerals, yeah. So radioactivity is a distinctive physical property as well. And an important one, because obviously we care about nuclear power plants and things of that nature. So minerals speaking of that, minerals have a lot of uses, right? And so one of the reasons we care about minerals is because we care about the things that we might be able to use them for. So whether it's iron, from which we make steel, or whether it's copper, from which we make all the copper wires that carry electricity, or aluminum for that matter that carry electricity. We use minerals every day of our lives. I'm using minerals right now inside this camera with its circuit board. There's a whole array of minerals in there that are making this whole video possible. So anyway, that's a brief overview of minerals. There's a lot more we could say, but thank you for listening, and good luck as you learn the language of the rocks. Till next time.